Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
He had said he would give us a really informal talk. This looks not so informal. But anyway, he's going to be talking about a lower bound for cooperative noisy broadcast.
So as always, it's really nice to be here. I've enjoyed my couple of weeks. I wish it had been longer this summer. Okay, so this is joint work with Navin Goyal, who is my PhD student, who's now at McGill, and Guy Kindler, who we all know is here. Okay, so here's the plan for the talk. I'll start with just a quick prologue about error-correcting codes. I'll reminding you of things which are familiar to nearly everybody here, but just as a little background. I'll introduce the cooperative noisy broadcast model and state our lower bound. And then I'll switch to a seemingly completely different model called generalized noisy decision trees and state a lower bound there. And say something about, well, it turns out that the CND, the lower bound in cooperative noisy broadcast, follows from the one in the other model. And so at that point, after I've made those remarks, we'll switch entirely to this generalized noisy decision tree model, which will be the rest of the talk. And so I'll talk about that bound. And there is one main lemma in that proof, which we'll spend most of the time in the second part of the talk talking about. Okay. So here's this, and I had a lot of trouble with slide text spacing, so suddenly this slide, when I changed the colors, the last line ended up on the next page, and I couldn't fix it. Okay. All right, so here's the part where I'll just quickly remind you of some very basic stuff about error-correcting codes, which, if you saw Madhu's talk, you don't need to be reminded of. So you have a sender who wishes to send a message consisting of n bits to a receiver, and the channel is noisy, so each transmitted bit is received incorrectly independently with probability epsilon. And an error-correcting code is a map which takes the thing you want to send and maps it to usually a longer thing, which is supposed to have some error-correcting capability, and then you have a decoding function which, upon receipt of a word, maps you back. And the sender sends E of X, and the receiver gets a noisy copy Y of what was sent, plugs it into the decoding function, and hopefully gets back what was sent. And so the goal is that the probability of decoding error is small, and also that the length of the code should be not much bigger than the message length n. All right, so the simplest code is the repetition code, in which the sender just sends each bit r times for some r, and the receiver just decodes each bit separately by taking the majority of all the bits that he received. And as is well known, if you choose the repetition parameter to be order log n, then you get a decoding error probability overall of 1 over poly n. So that's the chance that you will make any error on any of the bits if you do it. And the code length for that is n log n. But of course, we have Shannons Theorem, which says that you can do much better than that, which says that you can actually get exponentially small decoding error probability with a code whose length is only linear in the original message. Okay, so that's the end of the prologue. So next, let me introduce the cooperative noisy broadcast model. Whoops, there we go. So let's think about the same problem, But suppose that the bits x1 through xn originate from separate locations. Okay, so the setting is that you have broadcasters P1 through Pn and a receiver P0, and the ith processor for I bigger than 1 has the ith bit. And the goal is for P0 to learn all of the bits. Or alternatively, some specified function of the bits. Like he just wants to know the majority of all the bits, the majority value.
How can I code if I sit at different places?
That's the problem.
You'll see. Okay. So the noisy broadcast model, proposed by IGÇÖll, says that in each single time step, one broadcaster can broadcast a bit B, and every other processor receives an independent epsilon noisy copy of B. So everybody hears the bit, but some of them will hear it incorrectly. And we want to achieve whatever the goal is. Let's say that the receiver learns all the entire input with high probability while minimizing the total number of broadcasts. All right. So, well, we can just use the same repetition code. That we can do with separate bits. Each guy just repeats his bit order log n times. And same argument will say that the receiver will recover all the bits with high probability. Okay. Gallagher in 1988 came up with something better, which was n log log n. All right. You know, on the face of it, when you first hear it, you say, but how can you do better than just repeating? And we'll see in a second how you do better than that. And Kushelowitz and Mansour showed, well, let's say you wanted to compute the majority, then you can do that with only order n transmissions reliably, any threshold function. I'll just mention that the Kushelowitz-Mansour protocol is very sensitive to the assumptions that we had here. So the reception error must be fixed and known, and the errors must be independent. And if you deviate from that, then their protocol, then the properties of their protocol, the correctness, falls apart.
So fixed and known, I must know it. I must know the epsilon.
That's right. And if suddenly your channel gets more reliable, the protocol won't work. Okay, so it's kind of relying on the unreliability, on the predictable unreliability of the channel. So, you know, you could argue that's not a very good model then, and so there have been other proposals of more robust, yeah.
About this, so this was for any threshold function?
That's right.
So a fixed threshold function majority, they need to know the error
They need to
rate?
know the error rate, yes, in order to do their protocol for majority.
So just to see if I'm understanding, for majority, if each broadcaster broadcasts a fixed number of copies of his bit, and you just do majority on what you get, would that work with high probability? Or?
If you have log n repetitions.
What is the error rate? If the error rate is 1 over 10 and I send 30 copies, and take a majority.
You need exponentially small. I mean, you've got n bits to get.
Oh, okay, right. So you have to use the fact that actually the broadcasters can hear each other.
That's right.
Right. Okay.
Yeah, if you do majority in English.
Right, I understand. Then a constant proportion of the bits are noisy. You only allow some square root.
All right. So there have been some other proposals of models which are less structured. Okay, which, on the other hand, require protocols to be more robust, and they involve having some randomness and an adversary. And I won't go into it because it won't be really relevant to a talk. But there's work of Feige and Killian and recent work of Elon Neumann. I mentioned Gallagher protocol still works for these models, so his is not sensitive to these things. And positive results that even in these more, models where noise can be more perverse, you can do the OR function. Well, the original Feige-Killian paper did n log star n, which was almost linear, and then Elon got it down to linear.
Now what if I really want to have sort of the n bits?
You want to learn the entire n bits.
Yeah.
That's what the talk is about. So Gallagher's protocol did n log n. Okay, that's what we know so far. Okay, so let me tell you, here's Gallagher's protocol. So we saw the repetition is just log n, and now we want to see how did Gallagher, well, this isn't quite Gallagher's protocol. It's a bit simplified version of it, but okay, so the first thing you do is you take the processors and you split them into groups of size log n. Okay, and now you're going to have two phases for the protocol. In the first phase, each processor broadcasts its bit log n times. Okay, and now what is the idea? Each person in each group, each processor, ignores the bits that it hears from other groups. It only cares about its own group in this phase. There's only log n in its group. And so the repetition code is good enough for most processors to learn everything in their group. So what you can show is that with high probability for every group, 95% of the group correctly learns all of the bits in its group. Okay? Well, now once you're in that situation, now you can look at a group, and the group, basically everybody, except for a few bad guys, they all share the same correct information about their group. Now they can simulate a Shannon code jointly. So each one, let's say the Shannon code is one that multiplies the bits, is 10n. So everybody, each guy will be assigned 10 bits of the code to broadcast. And the guys who are bad, well, they're going to send garbage, but you have an error correcting code, so there aren't very many of those, so that'll get washed out in the error correction. Okay?
So when you, the second bullet, the high probability for every group, that high probability is like 1 over poly in log n, poly in n?
Yeah, I don't remember. I mean, you have to sit down. It's an easy
That's
calculation.
That's poly in n because there are about n groups, so it's good. It's poly in n.
The needs.
No, then it works because you have log n layers in a group. So when you're talking about the constant value,
So what I'll talk about today is the lower bound, which is a matching lower bound to Gallagher's protocol to show that, okay, so here's this clever protocol, and maybe, maybe you could do linear, and what we'll show is that you can't. That Gallagher's protocol is optimal up to a constant factor. So that sub epsilon, this is a lower bound that's n log n times some function of epsilon, which I'm hiding, and I don't even remember what it is. But do you remember what it is? Just linear.
I think it is.
Okay. So this lower bound is in the very regular error model.
Epsilon is
the error with which each bit is received.
It's the noise. There's a noise parameter, and that's the noise parameter. Okay. So this holds in the most optimistic noise model, which is the one where you have very regular error. So obviously it will work also in the noise models which are less optimistic, but previously there were no superlinear lower bounds known even for the more robust error models.
But the independence assumption is always negative, right? For the upper bound, that when I broadcast something, everybody is hearing independent.
Not for Gallagher's protocol. So okay, let me very quickly tell you what the Feiga-Killian model is. Okay, so the Feiga-Killian model you can describe as an error cancellation model, in which what happens is you fix your protocol, and now once you fix the protocol, and I want to emphasize one thing: the protocol, who speaks at time 7, the 7th player to speak, must be fixed. So you can't have adaptive order. You can't say, well, depending on what happens, either the 7th player will speak or the 10th, because, well, since people are hearing different things, you then might have 2 people broadcasting at the same time. So you have to fix who's going to speak, and now you fix that. And so that if your protocol is time t, then there are t times n reception events, which are each broadcast. So there are t times n noise variables, which are independent. Okay, so you design your protocol. Now imagine an adversary who flips an epsilon bias coin and determines some of these events are going to be faulty. But now he looks at your protocol and he can cancel some of the errors. Any ones he wants. He can't add errors, but he can cancel errors. Okay? And so that's the more robust, that's one way of describing this more robust error model. Okay, and Gallagher's protocol, you can see works. You can check works in that setting. Okay. All right. So now comes a context switch. What looks like a completely different model.
So it's quite amazing, you know, that the two bounds are the same.
Yeah, well, actually, we were surprised. You know, when we had the argument, or originally the argument, you know, there was a lot of slop in the calculations, and we didn't, you know, it was just trying to prove a superlinear bound, and then we figured, okay, we'll work it out. Maybe it'll be n triple log n or n double log n, and suddenly, I mean, n, you know, square root of log n, but n log n. So we were happy.
The two bounds actually just differ by the constant, right?
Aren't you surprised that they agree, or that these guys got them to agree?
You expected that such a team would get an even higher low bound.
Right. How much higher is your lower bound constant than the other?
Okay, so the next thing is next part is a completely different model. So now, for the moment, you have to forget the noisy broadcast model and learn a new model. So generalized noisy decision trees. Okay, so now there's only one guy who's trying to do a computation. Okay, and so you have a hidden input x, and the algorithm seeks to learn x, or f of x for some specified f. And what you have is a collection of noisy copies of this input x, and they're sitting there. And you have, the algorithm only has access to these noisy copies. Lambda is some arbitrary index set. Doesn't matter. It's just I need a name. This is the index set for the noisy copies. That's all. Okay. And so what can the algorithm do? The algorithm is allowed to make an arbitrary Boolean query to any one of the noisy copies. So I ask, you know, what's the majority value on this noisy copy? And what's the parity of this noisy copy? Now, the parity of a noisy copy is a pretty worthless piece of information, but I can ask whatever I want, and the queries are completely adaptive. I can ask this guy this guy that. May depend, what I do can depend on the previous answers.
And you have a huge reservoir of these noisy copies.
As many as you want.
You throw each one out after you query.
No, you can come back to it. You can come back to it, whatever you want.
But I can ask for, and I know which one is which one.
Yeah. There's
So I can say I want the fifth, and then I want the fifth again.
later on.
Do I have to
After you get some other information, you can go back to the
in
fifth.
between?
Why
do I
would
have
you
to
want the
forget
same
it?
one again?
Different Boolean queries.
But why not take a fresh copy?
Well,
it's
I
not
don't
clear.
know. It's not clear, you know. That, by the way, was a large amount of the time we spent on the proof, was proving that there was no value. We early on had a proof that of what you'll see, a lower bound in this model, if you only go to each copy once. And then we had to work a lot harder to prove I don't know any examples where it helps, but proving that it doesn't help is a problem. Okay, so as usual, this kind of decision tree, this can be represented by a rooted binary tree, and here is where I wish I was using PowerPoint with nice pictures, but I will draw a nice picture. Okay. So each node, you have a rooted binary tree, and each node, this is labeled by, 7 majority, which means go to the 7th, at the beginning, first step of the algorithm is go to the 7th copy and query the majority function, and then if the answer is 0, go to here. And if the answer is 1, go to here. And then you do the same thing. This is the 15th copy, and you ask what is x8? What is the 8th bit? And okay, and then you just branch, and then at the bottom you've got leaves which are labeled by output values.
What is 7 stand for?
Seventh copy.
The 7th copy. So
All the bits.
So you are labeled. You have a.
No, it's 7th.
Remember, you have a whole list of copies, and each one has an index. So
Each copy is of all the n bits.
Yes.
all n bits.
And each is independently flipped with probability absolute.
That's right. So you take the.
That's that an
It's the
arithmetic-
true input. It's the true input, with each bit noisified.
And can I come and actually switch it back to the right one? Do you have,
No, you can't. You have no access to these bits.
So there's no adversary now.
No.
That's right. There's no
So
access.
it's a stronger lower bound.
Right, 'cause it's not Florey's model, it's the.
Okay. And what we're aiming to do is minimize the number of steps, which corresponds to the maximum depth of a leaf. Yeah, by the way, when do I go to? What's the...
You can go, I don't know, until like 4:45
Okay.
or something.
All right. Now, well, these are called generalized noisy decision trees, so there must have been a noisy decision trees, which are the standard ones. This is a model of Feiga, Peleg, Raghavan, and IGÇÖll, where you can think of it. So their model, you didn't have, what you do is every time you make a query, you can just query one variable. What is x7? And the answer is noisy. Okay? But you can simulate that by this model by saying every time, I ask the 7th copy, I just restrict the queries I can make to be single variable queries. And it doesn't matter what copy you ask. And the queries are sort of obviously independent. I can ask of the 10th copy, what is x15? And then I can ask what's x13. It doesn't matter who I ask it because the value of the information is the same.
Except that now you have, the numbers are slightly different, right? Because you have n times lambda absolute value many.
Yeah, but I don't care. We're not paying for how many copies there are. The only thing we're paying for is the number of steps.
Oh, I see.
That's all we're paying for is how many times you have to, how many questions you have to ask.
So I can think of having infinitely many copies.
Yeah. Okay, so once again, you can see that by using repetition, by asking each bit log n times, you can learn the entire input reliably, which means you can compute any function. All right. All right, so here are some bounds. This is from the original paper of Feiga et al. So they gave a protocol for OR, which was linear, but then they showed that parity and majority function both require n log n. You can't do better. And obviously, the identity, learning all the bits, is the hardest function. That also takes a lot. Okay. Now, generalized trees are in principle.
The output function is not 1 bit.
What? The identity function is not a 1-bit function. That's the n-bit function. That's.
So but the queries have to be 1-bit functions.
That's right. Queries still have to be 1. Okay. All right. So, well, I haven't explained the relationship between this model and the cooperative noisy broadcast. We will explain it in a minute. But it turns out you can take the protocols that Kushelevitz, whoops, that's not KM, KM, excuse me. Kushelevitz and Mansour, if you can take their protocols and convert them into ones for OR and majority that work in this model. All right. So what we're going to prove here is that even with these generalized trees, you need n log n queries to learn the whole input. Okay? And what we thought was, and our next project was, that the parity function ought to be hard. And there's something about the way our proof is structured, it really looked like it should be tailored to actually show that parity is hard. And so that's what we set out to do. And well, I put a question mark here only, so it turns out that we found a protocol for parity in this model that's theta n, but I put a question mark there because as I was thinking about it for the talk, I had some questions about it. So I have to talk to Guy about it after the talk.
The question mark should not be in the parentheses, it should be after the theta of n.
That's right. That's right.
Yeah, I was wondering that too. I thought, well, that might be the person who helps you get out of the question mark after
Okay.
theta then, right?
That might be.
But I thought that you don't know yet who will help you to prove the theorem, but you know it's true.
Okay. All right. So more precisely, the bound that we get is that any generalized noisy decision tree that covers the entire input with high probability must have depth, at least epsilon to the fourth n log n, where epsilon is this independent error parameter. And so for this result, for the reasons that will become clear later, the dependence on epsilon is important. The fact that it's polynomial in epsilon is important. And I'll say the lower bound also, I haven't defined what a randomized tree is, but it's the usual notion. If your algorithm is allowed to flip coins and you formalize the model, then that doesn't really make a difference.
With hypothetical? To 1 minus little of 1?
110, 1 over 100, any constant. But I mean, it's probably better than that. You know, we haven't worked it out, but you know, so. Okay. So the next part.
I see. So what if I only require that it's 1 over log n?
If that you get it correctly with probability 1 over log n?
Yes.
Yeah. So we. At least I have never sat down and figured out what the limits are. It definitely will, we prove our bound will probably show something that, you know, you can't even, my guess is that you can't get error probability 1 over n to the 1 minus epsilon or something like that. What do you think? Do you have any idea? I never thought.
Probably do have an idea, but not.
No, I mean, it's just a matter of chasing through the arguments and seeing what it gives, which we haven't done. Okay. All right. So I've given you 2 models, and you've probably forgotten the first one by the time we've talked about the second one. And so now this is the dangerous part of the talk, where we're going to talk about, we're going to be context switching between 2 models, and in fact, there'll be a third model I will introduce in order to switch. So what I want to show is that the GND tree lower bound implies the cooperative noisy broadcast lower bound, or at least give you a hint as to why that's true. Okay. So here's the idea. The usual way, if you want to, if I have a lower bound for GND trees, and I want to show that it gives a lower bound for the other model. So the way you do that is I show that if I have an algorithm in the first model, I can convert it to an algorithm in the second. Okay, and that means therefore a lower bound in the second will imply a lower bound in the first. Okay, so here's what we show. If you have a protocol, so that remember the cooperative noisy broadcast, you got this bunch of protocols, and we're counting broadcasts, a bunch of processors. So suppose you're doing identity function of length n. The noise parameter is the error parameter for each thing, and it takes kn broadcasts. Then if you give me a protocol that succeeds, then I can convert it into a GND tree whose input length is half, n over 2. The noise parameter is a lot smaller. So the GND tree will only work if the noise parameter is considerably smaller, delta to the 2k, where k is this thing that you're multiplying n by there. But the number of steps is about the same.
What is k?
Anything. Think of it as log n. Okay. Which is what. So what's going to happen is if you take k equal log n there, then you will see that this will lead. Let's see, what am I saying here?
To 2k is 1
So
over log
it's
n.
easiest to think about, you have these, broadcasters, each has 1 bit, and they have k times n broadcasts, to spell. So one obvious thing they can do is for each one to broadcast its own bit k times. Once they did that, everyone else.
Yeah, I will get to that.
Okay,
Yeah,
sorry.
yeah. So I'm saying this. Right now I'm just stating the relationship, and then I will say something about why it's true. But all I'm saying is, I'm about to say something about a way to convert such a thing into this. And now, yeah.
Well, okay, go ahead.
So now if you take k equal log n here, then it will say that if you had a CNB protocol which worked in this, then you will get, let's say not log n, but log n over 100 or something like that. Then you will get something which is a GND protocol which works with a fairly small noise parameter, but that's going to be, let's see,
Polylog.
Polylog, right? And
It's not polylog, it's like log n to the epsilon.
log n to the epsilon, that's right. And so, I'm having a little trouble saying it, but if you just plug in k equal log n over 100, then you will see that the protocol you get here violates the bound.
And what is delta?
What?
And what is delta? A half or what?
Think of delta as some constant here. Okay, a small constant. Whatever noise parameter, 1 over 100. Okay. All right. Then you will see that this lower bound here will give this lower bound. Or if you had a better protocol than this, then you would violate the lower bound. And that's just a routine
So you can simulate the small noise by sending each bit log n.
That's right.
Yes.
So you just pay an extra log n, which seems a sense, because then why couldn't you why couldn't you get using this approach lower bound even higher than n log n?
Yeah, it doesn't quite, so it does look like that because if you, the problem is that as soon as you make k too big, this error parameter is going to become more than log n. I'm sorry, it'll be less, the error parameter will be polylog n, 1 over polylog n, which when you plug into this bound won't be constant, it won't violate anything.
So if you had an n double log n, then you get an n square root log n lower bound for the GND tree, for example, something like that.
But in other words, it's very sensitive. This thing is very sensitive to k, and if k is 100 log n, that's not going to be that won't contradict anything. 100 log n won't contradict the theorem. You just have to trace through, and you will see, because the error parameter is going to get really, really tiny. The noise parameter will get really tiny on this side. Okay, so let's just very quickly see. So I start with this cooperative noisy broadcast protocol, and I want to convert it to the GND tree protocol. So you've got all these processors. All right. So the first thing you can do is the protocol could have different people speaking a different number of times. So first we'll regularize the protocol, have everybody speak the same number of times. And what you do is you take everybody who speaks more than their share of times. Their share is k times. So anybody who speaks more than 2k times, I'm going to get rid of them. And the way I'll get rid of them is I'm going to just fix their bit to 0. And I'll tell everybody, I'll just announce their bit is 0. That way you get rid of at most half the processors. So you still have to figure out the other n over 2, and everybody else is speaking at most 2k times. And anybody who speaks less, just let them say whatever they want. So you can
say it's not just a function of my own bit, but what I've heard, right?
Right. But if I fix the bit of everybody else to 0, then I can sort of simulate. Everybody can simulate what they're going to do. You have to think about that, but it's not. So I'm not giving you a proof. I'm just telling you how the proof goes, and the steps. You just have to think about that. You can simulate the noise with your own private randomness, and you can, so you can simulate the protocol. Okay. So now we have this protocol where it's a regular protocol, and now I have to introduce another model, which I'll call the semi-noisy broadcast model. In that model, processors make 2 types of broadcasts. Well, they can either broadcast their own bit, and that's noisy, or they can broadcast something depending on what they've heard, but independent of their own bit, ignoring their own bit. And that is noiseless. We promise that that's noiseless. So now what you can show is that if you had a protocol in the CNB model, then you can convert it to something in this semi-noisy model. So you can kind of separate out the talking about your own bit and talking about what you've heard. Okay, that's not hard, but I'm not going to tell you how to do it. And you end up with something which is again regular. So this 2K, 4K means that the number of times everybody announces their own bit exactly 2K times, and everybody talks about the other bits exactly 4K times. Okay, so now we have this kind of protocol. Now the next thing you can realize is that in that setting, you might as well make all the bit announcements right at the beginning. So everybody you just take your protocol, and any announcement about your bit, you just move to the beginning, and you can see that's not going to change anything.
Wait, but I was allowed to change. Oh, I only have one bit. I can't adaptively announce different things.
Well, I can, but those are the other kinds of broadcasts. So I'm saying the type 1 broadcasts are just announcing your own bit. Those are the only noisy ones in this model, in this intermediate model. And then the other ones are talking about what you've heard, which are the noisy bits of other people. And
you say the item just gets more power if you learn the other ones all first.
Exactly. That's right. Okay. So now we have a two-phase protocol. Everybody says their bit 2K times. Yeah.
Why is talking about somebody else's bit has to be independent from your own bit? It's not like that in Gallaghers.
Doesn't give a reduction.
You just have to do. I'm just saying. So that requires 5 or 10 minutes that I don't have. Okay. So that's all I'm saying.
But you agree that Gallaghers protocol is not like that because they are building a code from the information they share. This you don't allow in this. So you say Gallagher could work even in this model.
That's right. Yeah. I'm just saying there's just a transformation where if I can make sure that all these other broadcasts, I can sort of separate things out. I'll just give you a quick hint that'll make you happy. When I speak, what I have is, let's say, what I have is generally a function of my own bit and everything I've heard. So what I do is I announce, what would I announce if my own bit was 0? What would I announce if my own bit was 1? And I announce, and that's the two. So I just give you those two pieces of information. I may have to, and that's basically it. Okay. So every time I have to speak, I just, give those two things, and that's both pieces of information are independent of my own bit. Okay. All right. So now in the first phase, you've got these epsilon to the 2K. So now what I'm saying is, if I announce my bit 2K times, it turns out you can sort of simulate that by just announcing one bit with a much lower noise probability. Namely, if I lower the noise, if I imagine that the channel noise was improved to epsilon to the 2K and I just announce my bit 1, then that provides as much information to everybody, at least as much as my 2K noisy bits. Okay? So we replace it by that. Now, if we do that, then at the end of the first phase, everybody has a noisy copy with this noise parameter. And so now these play the role of the noisy copies, and you can simulate the rest of the protocol by thinking of it as queries from a generalized noisy decision tree.
So the number of copies is the number of players in this.
That's right. Okay. So now we'll talk about the. Okay. So now at this point, we forget protocols for cooperative noisy broadcasts. The entire rest of the talk is in the GND tree model. Okay. So which I will. That's this picture again. You got a bunch of noisy copies. I can ask arbitrary queries to the noisy copies. Okay. So the first part of the proof is reduction to the main lemma, and we'll have to get there. So let's remember what we're proving. We are proving that if you can recover the whole input, then you need depth at least epsilon to the 4th n log n. All right. So we have to prove a lower bound on the depth of a randomized GND tree that on every input evaluates identity with high probability. So there's the standard trick of, instead of, this is like a worst case, on worst case input, you look you fix a probability distribution over inputs, and then it's enough in that case to work just with deterministic algorithms. Okay. And so we're going to use the uniform distribution over inputs, and now we fix one deterministic GND tree. You present me with, here's the one that you think works, and I'm going to prove to you, I'm going to prove to you that it must have depth at least epsilon to the 4th n log n. Okay. So we're going to be analyzing a probability space, and the probability space is, well, it's determined, it consists of the random input and all the independent noise vectors which correspond to the different copies. So that's the probability space we're analyzing. Now, a point from the probability space, once I specify the input and I specify all the noise vectors, then you know exactly what's going to happen on this tree. You can answer it. So a point from omega will determine a root to leaf path in the tree, and we'll have certain random variables. X is the random input, and lambda, and I think I'm not consistent. Sometimes lambda is superscript and sometimes it's subscript, but n lambda is a random epsilon noisy n vector indexed by lambda. Okay, pi is the random variable which is the final leaf, the leaf that you end up in. And for each node v, we have an event, visit v, which is the event that v is visited. Okay, so that's some event in this probability space corresponding to each. All right, now, so how do you prove a lower bound? Well, people in the business of lower bounds, here's what you do almost all the time in these things. Maybe not explicitly, but this is pretty much what you do. You have some computation model, and then you introduce some measure of progress of the computation. And the measure of progress kind of depends on the state of the computation, which consists of the input and where the algorithm is, which in our case is going to be the input and what node you're at in the tree. And the progress measure sort of quantitatively says how much have you learned towards what you're trying to learn. Okay, so you want some real number measure which tells you this. And the properties you like of your progress measure is that initially it's 0. And, well, for some delta, you have some bound on the incremental change in the progress measure. You show that each step of your computation only increases the amount of information by a most delta. And then, on the other hand, you show that a good algorithm should finish with this progress measure large, let's say with high probability. And so then your conclusion will be any algorithm requires B over delta steps. Okay. So we want to find a good progress measure for GND trees. And so in this case, the progress measure, as I say, should depend on the input in the current node. And we want B over delta to be omega n log n with, well, the epsilon to the 4th. Okay. So here's a first candidate, which is a pretty natural one when you think about it. You have to think. All right. So you have to stare at this a second. You have the probability that, suppose I'm at node V, and I want to know what is the probability that this is a Bayesian calculation. Given that I'm at node V, what is the probability that my input was X? So that's kind of, when you're at node V, based on the fact that you're at node V, you started with the uniform distribution, you have a new distribution over the inputs. And what should happen as you're progressing in this computation is that should be concentrating on some particular input. Eventually, when you're done, if you can say reliably, well, the input is 001, 001, that should mean that this probability has gotten very close to 1.
For the right X.
For the right X. Okay? So, okay, well, it's easy to see that this thing, that the additive n was to make sure that the progress measure starts at 0. Initially, this is, for every X, this is just the probability is 2 to the minus n, log is minus n, so that's 0. And in a good tree, you should arrive at a leaf, that v should be a pi, you should arrive at a leaf where, well, I didn't say what little x is here, but where for some x, this probability, in fact, for the right x, you know, if whatever your input is, you look at what your input is, and you want to arrive at a leaf where you can be confident that that was the input, which means that this a priori probability is now close to, or a posteriori probability is now close to 1. Okay? So therefore, you would expect that the value of this thing as a random variable, that the value of this thing at the leaf you end up with on this input x should usually be close to n. Okay, so you need to make n units of progress with this measure. And so for our lower bound, we would like to prove that the increment in this thing is something like 1 over log n, the typical increment. But unfortunately, the incremental progress for this thing can be like omega 1. And if you look at, just look at what happens if you read all the bits of one noisy copy. Okay? Then you will see that this progress measure actually will increase by omega n. You'll already make a constant fraction of the progress with just n reads. Okay? So that doesn't mean you couldn't use this progress measure, but you can't use this paradigm, and the approach, it's going to be a lot messier, and we couldn't do it. So we had to look for another one. Okay, so here's the progress measure we ended up with. And okay, so what you're going to do is, as you look at the progress, so for a particular input x and the node v, we're going to say that you have made progress in proving that x is the input, that little x is the input, by comparing this a posteriori probability for x to its neighbors. This means this is the mod 2 sum with the ith unit vector. So you just look at the neighboring points and you say, how well have I distinguished x from all its neighbors at this point? All right, and so that's what this thing, so this is, so the PMI is just looking at one of them, and then the progress measure is going to be the average of the PMIs.
So the intuition is that when you make a query, it really differentiates between x and all the many other inputs that are very far from x. So, you know,
the hard inputs to differentiate you from are the neighbors. So we're going to concentrate on how well you differentiate yourself from your neighbors. That's now, this particular functional form turns out to have all kinds of lovely properties, which we didn't know when we started, but you know, they kind of, as we worked with it, it just kind of worked more and more beautifully as we went. So, but here's the first lovely property of this thing. Well, wait, before we do that, yeah, okay. So this is the first thing is that we want to prove that a successful algorithm must have a large value of the progress. And so we have this lemma, which is not that difficult, but I won't have time to say anything about it. But it's really, you know, it's a paragraph. And you prove that in a successful algorithm, you need to finish, the progress measure usually ends to be about natural log of n. Okay? So the probability that it, let's see, what am I saying here? If the probability that it exceeds this is less than gamma, so if this is less than this, then the total probability of success is at most 2 gamma. Okay. So let's focus on, we have these standard queries. Those are the easy queries which just look at one bit at a time. Okay, so let's look at that, and let's see how this progress measure behaves. And it behaves really nicely. Okay, so suppose you're at a node V and you just ask a fresh noisy copy of xi, by which I mean you haven't asked anything of this copy before, or at least only other bits, but you haven't. So this bit is independent of all the information you've learned so far. And you ask xi, and, well, what's going to happen? Well, whatever xi is, if it's 0, then with probability 1 minus epsilon, you'll get an answer 0. And otherwise, you get a probability 1. And by the way, if you get an answer, the wrong answer, well, intuitively, that's given you negative progress. It has misled you. So you're actually going to lose progress if that happens. Okay, and well, if you work out what this is, then the progress measure changes by exactly this thing, independent of the node V that you're at. Okay, and so this is about 1 over n times a constant. This is 1 over, and this is a negative constant. If you get the wrong answer, then your progress goes down. Okay, but it's very nice. So it says the progress is 1 over n times a constant, independent of anything. Well, that automatically gives you a lower bound for standard noisy decision trees. There are other ways to get this lower bound, but this tells you since the progress per query is only 1 over n, and you've got to make a total of log n progress, then you get your n log n lower bound in this case. Okay. So now,
why don't you give polynomial in epsilon? It's clear. This argument.
Why does this argument give?
Yeah, you wanted to get the lower bound n log n times the polynomial in epsilon. So is it clear why that's what you get?
Log of 1 minus x. That's log of x.
Log of epsilon, polynomial in log.
That's too good.
What?
That's too good.
But this is for this much weaker set of.
So you can get for this much weaker.
A better dependence on epsilon.
Like log 1. Okay.
Okay. All right. Now, what happens with general queries? Well, unfortunately, things are not quite so nice. So, first of all, the value of a general query, what happens to the progress measure, can be highly dependent on the node, the information you've gathered from a node. Okay, and it could be significantly larger than 1 over n in some circumstances. Okay, the intuition is that at a typical node, the expected incremental progress of a general query is order 1 over n. That's kind of the intuition that's driving what we were trying to do, but the proof doesn't look like that at all. I mean, so one could probably tease that out of the proof, but it's not going to be evident. All right, so well, what is it that we want? So what I know is that I must end up at that I typically, in a successful algorithm, end up at a node where the progress value is like natural log of n. Okay. Now what I would like to do is prove, essentially, I look at the progress value at the leaves. So I look at the progress value at all the leaves, and I think of that as a random variable. And I want to prove that if the depth is not large, then this progress value is small, which means I'm trying to prove a tail bound, that the probability that the progress value is large is small. Okay, so that's what this thing says here. For every fixed input x, you look at the progress value at pi. I think I've changed notations by putting PM as a subscript, but okay. The progress, given that the input was x, I look at the probability that the progress exceeds b, and that's at most this. So if you take b to be, let's say, 1/2 natural log of n, then this thing, let's see, if I take b to be 1/2 log n, well, in a successful algorithm, I need that this probability should be large, because probability that you should be close to log n. So in particular, you should be at least 1/2. So this bound should be at least 1/2. And so turning that on its head, you get that the depth, therefore the depth of the tree must be large. Yes?
If you're fixing x and the measure just trying to check whether you distinguished well x from its neighbor, isn't it like computing the O function, which has a linear time protocol?
The answer is, so that's the convincing thing, but it doesn't, it's not quite the same as, see, because what happens is, you're not, I mean, you're trying to distinguish it, but you're using this funny measure. I mean, you're not really reducing it to solving OR.
So what happens when you run this analysis on the linear time decision tree for the O function?
The problem is this analysis does not work for any Boolean. We don't know how to make this algorithm work for any single-valued function.
It's actually very delicate. In an OR function, well, you have to define the distribution on the inputs where you start.
But here you fix, in this lemma, until now I was happy, but here you fix x. This lemma talks about particular x, like the O0.
The point is that, in an OR, if you want to distinguish between the 0 vector and all the other vectors, for the problem to be interesting, the probability of 0 must start as half.
But where do you see this here?
The point is that it has a shorter way to go from 1/2 to, you only want to increase it from 1/2 to 3/4. While here, at the beginning, you start with the probability of x, which is much smaller.
Relative to its other, if you condition on the,
is greater.
if you condition on the input being either x or its neighbors, then the uniform distribution gives you a distribution where the probability on x, initial probability, is 1/n+1. So you're initially much more likely to be one of the neighbors than you are of x. And you somehow, and in the OR function, yeah, it's...
so you would need
this lemma
n.
What?
Here, the progress that you need to make is log n. While in the case of OR, the progress that you need to make is constant.
In fact, you don't have to make any, in some sense, you don't have to make any progress.
Yeah.
What I'm saying is if you condition on it being x or its neighbors, you take the uniform distribution over inputs, you condition on it being a particular x or its neighbors, then you already know that with high probability that if it's 0 or its neighbors, then with high probability you know that there's a 1 there.
I understand this. I'm just saying the main lemma doesn't condition anything. It states something for every x. Like, for example, for the O0
Right.
one. So,
but the probability weights in the PM of x function depend on the distribution, right?
I think let's take this off.
Okay.
All
I
right.
have a different question, which is, but I'm happy with this slide too. In B, it just looks like the trivial first moment. Probability that m larger x is bounded by the expectation divided by x.
What? I'm sorry. So this. Oh yeah. Good. It looks like a trivial. So the question is, where do we get this main lemma? And right. So the first thing to try is a first moment bound. Let's try it. I'm glad you brought that up. Okay. So. Okay, so we're going to have the main lemma proof, and now everything from now on is just this main lemma. Proving a tail bound for the value of the progress measure when you arrive at a leaf. Okay, and since we are conditioning on a particular input, everything by symmetry you can fix that input to be the 0 input. So we'll do that. So now the only randomness is the noisy copies, and those noisy copies induce a stochastic process from root to some leaf. Each vertex, so now I'm going to drop the dependence on x in my progress measure. It's just the progress towards deciding 0. That's PM of v. And let's write PM star for the random variable, which is the progress value of the final leaf. So that's what we're trying to prove a thing on, and now we'll give an overview, and that's probably what I probably will not get to a closer look at parts of the proof. So proof of the main lemma overview, we want to prove a tail bound for this thing. And the obvious approach would be to obtain upper bounds on the expectation invariance of PM star. So first thing we do is we look at the case that there's just one noisy copy. We say, okay, what could you learn if there was one noisy copy? And what we can show in that case is that the expected progress is at most the entropy of the leaf. Now this leaf there's some distribution over the leaves, and there's an entropy, and it's easy to see that the depth of the tree is at least this entropy. So this gives it a lower bound on the. So this gives us an expectation which is the depth divided by n times epsilon cubed in a second moment, which is the expectation, or the depth over n times epsilon to the fourth, but only in this special case, single noisy copy.
Can you go back? What did you originally want to prove?
Yeah, so I will say, so if I put depth here, then it looks like the first moment bound is exactly what you need. But I'll say,
to the fourth, so it's actually better.
That's right. I mean, I just want polynomial in epsilon, but I don't really care about the power. But yeah, that's right. It looks even better. Okay, and we don't even need the second moment. Looks like. Okay. So, but wait, but that was only for the single noisy copy case. So we now next have to somehow generalize this to the general case. So we have the progress that you make overall, and it turns out that there is a natural way to split that progress into a sum of the amount of progress you make due to copy lambda. And intuitively, and this is pretty much what it is, you look at the progress as you go along, and you look at the nodes that were labeled lambda. Those are the ones where you queried copy lambda, and you look at the amount of progress you made in those steps. And that's the PM lambda. So you can write it that way.
How large is each of these PM lambdas?
What's that?
Do you have an upper bound on the PM lambda?
Well, so now it turns out that you can, and you have to play around a little, but you can reduce the problem of bounding the expectation of PM lambda to the single noisy copy case. You can kind of hold fixed all the other noisy copies and analyze the single noisy copy. And that's one of the nice things about this progress measure, is that you get this additivity for different noisy copies. All right, so using the decomposition of PM star and the single noisy case, well, we get exactly this. The same thing. So everything works out very nicely. And this looks like more than enough for the desired tail bound. If you just look at this guy and you see what you need here, what you're asking for here, it looks like it's exactly just Markov bound. But we don't have it yet. And the reason is you can't use the first moment because PM star can be negative. We can make negative progress along certain branches, and we don't have a good lower bound. If we could prove that, well, you know, the probability that it's negative is small or something like that, anything like that, if we had bounds like that, then we would be able to do that. But we don't. Okay? And the second moment, the problem is that, well, we have a good bound on the expected square, but only of the contribution of lambda. But if we want the variance of PM, we also need a bound on those, and intuitively that should be small. That the kind of the progress, the amount of progress you make due to one noisy copy ought to be sort of independent. But the problem is you can tailor your algorithm so that, let's say, based on what happens with, you query one noisy copy, and then depending on what happens to that, you, in one branch, you query a different noisy copy, and then you query a different one, so you can artificially cause these things to be larger or something like that. So
how much progress for single lambda could you possibly make?
the total amount of progress that you can make from a single lambda, I think is order 1. Order 1.
Why can't they now just use the semi-martingale bound?
What's that? Oh, no. Is that why I said this right? From a single copy, you can...
You need several queries, but you can make all those one.
So what if I apply Azuma Höfting to that?
Well, okay, so we tried Azuma like things. The problem is that, I mean, at least I don't know the assumption. You have all kinds of dependence. You have all kinds of dependence in the steps of this thing. It's not a martingale because you can go back. This is where the problem of going back and querying copies that you've already used be. That was why, in fact, if we had the case that you query different copies, then in fact the original argument we had was a martingale. But you don't even need that. You just
anyway, Azumas would give us very strong concentration, which is not true here. We just want to be bound, but we can apply Azuma, then we can prove exponential minus p.
That's right.
Then it's too much.
Okay. So what do we do? Okay, so first thing we do is we refine PM star, the progress, even farther. And the refinement is you kind of define a random variable which represents the contribution of each particular node. And I'll tell you what that, again, since I have to skip the more details, I'll give you a couple of more details really right now. It's kind of naturally what you'd expect. So if you do not travel through node V, then node V gives no contribution to the progress, so then it's 0. And if you do travel through node V, well, then you travel one direction or the other. And in one direction, you'll increase the progress, you'll change the progress this amount. So it's a random variable which is 3-valued. PMV is 3-valued. It's either 0, or it's the amount of progress you make along the branch if you go left or right, depending on that. Okay? So that's PMV. And you can then define PM star. The whole thing is the sum of all these progresses. Also, the progress that you make from copy lambda is just this. Okay, but now we're going to split PMV into two components. So we take the progress that you make at V and we're going to split it into two things. And the way QV, and I'll tell you what QV is. So let's look at this thing from a particular node V. And again, we have the progress at node V is 3-valued. If you don't go through V, it's 0 progress, or it's the amount of increase or change in progress in going from here to here. If you go, okay. Now, when you arrive at V, assuming you arrive at V, there's an expectation to the amount of progress you're going to make, which is just the conditional probability that you go left, given what's happened, times the change in progress. Okay, so that conditional expectation you can calculate. And that will be the value of QV. So QV will be 0 if you don't visit V, and it will be equal to the conditional expectation of PMV given that you visited V. So it's just a 2-valued thing. And, and R will just be PMV minus QV. So it's, how much. Now, this is, you have a certain expectation of how much progress you'll make here, and now you have the actual progress, so you take the actual progress minus the expected progress at that node. So now, the total progress is now the sum of those, and we'll get a separate tail bound for each one. So the tail bound on Q, well, the way we've defined it, expected of QV is exactly the same as the expectation of PMV. And so the overall expectation is the same. But the nice thing is that now the fact QV is always non-negative. And that you can do because if you calculate what it is, you will see that it corresponds to a relative entropy of certain two distributions, and that's always a non-negative quantity. And therefore, we already have the bound on the expectation, and now we can apply Markov, and we get a good tail bound on Q. So now we have for R, well, the expectation of R is 0, because it was the difference between these. So now we have to do a little bit of work. It is not apparent what happens to the variance, and you have to do some amount of work to show Whoops. Oh, that's not. That's PM lambda. So we already calculated the variance of PM lambda. And the variance of R lambda is at most a constant times the variance of PM lambda when you make this change. Now remember, the problem that we had before was that we couldn't prove the independence. But now, because of this expectation being 0 here, it turns out that's just what we need to prove that the covariance here is 0. So now we get the variance, and now we can get a good tail bound on R with Chebyshev. Okay. So, well, that's a summary of all the main steps, which was so we get upper bounds on expected PM. Whoops, this isn't quite right. That should be, forget about that lambda. That should be PM star squared for the single noisy copy. We decompose PM star into the sum of the contributions due to the lambda, and then we use this thing to get bounds on this, and then therefore bounds on on the expectation of the whole thing, and the sum of those. Then we further decompose PM into PMV, and then we split it into these two contributions, which we can then separately bound, and there are these properties that I just said. Okay, so now a closer look at parts, which you will be spared. And so main open problem. Main open problem is prove a superlinear lower bound for some single bit output function. And one of the things that we're discovering in trying to do this is that it turns out that you can develop a fairly rich class of functions. It's like of functions that you can compute. So you can compute such a function, and then you can compute a function which you can get by composing functions of these types and stuff like this. And you find that you have this class, and you run into the same kind of problems that you try to get in proving any kind of circuit lower bounds, which is that you've got some completely unrecognizable class, complicated class of functions that it's hard to draw a limit, and even we don't even have a candidate at this point for a function for which to prove a lower bound.
So this is in the generalized noisy decision tree model, or in the other, or both?
Well, either. Okay.
So I think we don't even know that a random function.
That's right.
That a random function would be hard.
Can't you use this progress measure in opposite way? So in other words, you want to develop some algorithm to find the right answer, then you want to increase this progress measure and at each step by order 1 of
Right.
10.
So this progress measure is tailored to the function, which is the identity, proving just this identity function. We don't really, I mean, there are guesses as to how to modify it for other functions, but we kind of know everything there is to know about this identity function. So we would...
Even for this identity, you can use...
Well, but the identity function, there is a trivial algorithm that does n log n, right, which is just repeat every bit n log n times. So yeah, so we don't have to.
We should remember that there is a talk tomorrow at 1:30 for the amount of